All right. And our second talk of the day will be from Patrick Jefferson from MIT, and he's going to tell us about new resolutions for F-theory and chiral matter in standard model-like constructions. Take it away, Patrick.
Okay. How long do I have, by the way? So it's supposed to be, I'm going till 11:57, is that it?
Yeah.
Or sorry, 5 past that, so 12:02 and then 5 minutes for questions. Is that the idea?
Yeah. That's a great breakdown.
Okay. All right. So the title of my talk is New Resolutions for F-Theory and Chiral Matter and Standard Model-like Constructions. And the talk is advertising and sharing some schematic aspects of an upcoming work that will hopefully appear in the archive soon with Waddy Taylor, who's, I believe, is in the audience today, and Andrew Turner, who are both at MIT. So a few words of introduction and some motivating comments. F-theory, as I believe many people in the audience, perhaps everybody, is very much aware, is a very useful and powerful toolkit for constructing standard model like vacua and string theory, specifically in type 2b. And the setting that I'll be discussing today is F-theory compactified on an elliptically fibered Calabi-Yau fourfold. This has been studied by a number of authors. I've listed many here, and I'm sure that I've omitted some, so I will offer my apologies in advance for those who I haven't acknowledged. And in particular, there's been a bit of a resurgence in interest with possible connections to both phenomenological applications and swampland-like questions. Maybe I should say landscape/swampland. And as far as landscape questions are concerned, one of the things that we require, and which F-theory provides, is tools to study large families of vacua in a systematic and tractable manner. So what I'll focus on today is a particular sharp question that one can use to scan the landscape for vacua with possible standard model like matter spectra and symmetries. And of course, the proper chirality. And this thing, namely, that we'll look for are particular flux backgrounds, G4 flux to be specific, that are compatible with various consistency conditions that we impose in order to preserve desired symmetries in the vacuum of interest. And what I'll talk about today is a new procedure, which is, although the procedure is new, it's really a synthesis of known techniques that can be used to compute flux backgrounds for large classes of hypersurface Calabi-Yau fourfolds. And this in particular includes cases of non-toric bases and also non-Weierstrass model formulations of F-theory vacua. And the motivation and hopefully the end goal of this discussion and the generalization of the techniques, or rather the synthesis of techniques that I alluded to, is heading towards computations that are relevant for a particular family of standard model like vacua characterized by the symmetry group SU3 times SU2 times U1 mod Z6, which were constructed and studied by Nikhil Raghuram, Waddy Taylor, and Andrew Turner in a recent paper. So the plan for my talk today is, given the limited amount of time, I'll have to be schematic and somewhat brief in what I say. I just want to talk about 4 things. The first of those is introducing the notion of tuned gauge symmetry in generic matter, and where this particular standard model gauge group with a discrete quotient fits into this picture. The second thing I'll discuss is resolving this family of models in F-theory, and moving to the M-theory dual description, compactified on the resolved Calabi-Yau fourfold. And then I'll move on to discuss some generalities of computing flux backgrounds in the setting of such resolved Calabi-Yau fourfolds. And finally, I will end with a few selected, just a couple of selected results and some future prospects. So to begin, let me just be very clear about the setting in which I'm going to be discussing the construction of various vacua, and that's going to be a singular elliptic. So my starting point is a singular elliptically fibered Calabi-Yau fourfold, defined in a very much canonical form of a Weierstrass model. So we can view it as a hypersurface Calabi-Yau given by the vanishing locus of this particular cubic equation in a projective bundle where the fibers of the ambient space are P2. And something very useful that can be done in this setting is to tune the sections F and G, and consequently delta, which is constructed out of F and G, in order to engineer a Calabi-Yau manifold with a particular gauge symmetry G. And one reason this is of interest, of course, there's other ways to arrive at various gauge symmetry groups in the F-theory constructions, but the reason that this is a technique of interest is because it leads to a fairly universal local characterization of the structures that one would expect to see if one demands that the vacuum have a particular gauge symmetry group G. So a question I'll ask in the setting is, when is a particular matter spectrum, which I'll denote by R, generic? And an answer, one possible answer, not necessarily the only one, but one possible answer was given by Taylor and Turner in a recent paper where they discussed the notion of generic. Well, they introduced the definition of generic matter. This is a working definition in the context of F-theory and also 6D supergravity. And the definition that they use is, for fixed gauge symmetry G and a fixed number of tensors, a matter spectrum R, which is generic, is on the branch of moduli space with highest dimension.
Hey, Patrick?
Yes.
For me, at least, it still says you're on slide 2. It hasn't advanced at all.
That's very interesting. Thanks for letting me know. That's quite important. Let's see. Wonder what the issue is here. I'm changing slides now. Can you see that? You can't see the change, right?
No, can't see the change.
Let's see. It should be working now, I think.
There it went back to your intro.
Okay. So this is the slide I was just discussing. I'll leave it up for just a couple of seconds to, in case anybody, well, I'm assuming nobody was able to see what I was just referring to. Right. So this notion of generic matter can be defined in the context. It can be given a precise definition in the context of 6D compactifications. And a question that's natural to ask, given a notion of generic matter such as this, is whether or not the minimally supersymmetric standard model spectrum is generic for a particular realization of this standard model gauge group. And it turns out that there's two choices, at least, that are very obvious. One choice doesn't involve a discrete quotient by Z6, whereas the other does. And given this definition of generic matter, the MSSM spectrum is generic for the tuned gauge symmetry construction involving the Z6 quotient, but not for the other one. This was shown by Taylor and Turner in a follow-up paper. So I'll be discussing this construction today. And the idea is that the standard model spectrum there in 6D is appears to be generic according to this definition. So one might postulate further that this this construction can be extended to a higher dimensional base, leading to 40 compactifications, in which the same spectrum is also generic, and this can be used subsequently as a playground for trying to construct this particular family of standard model like vacua. I should say this construction is defined by some characteristic data, which I'll present in the form of divisor classes. They're dual to line bundles that the base is equipped with. There's the canonical class K. There's a divisor class sigma 2 and sigma 3. These correspond to the SU2 and SU3 gauge symmetry factors. And then there's another line bundle Y, which I'll for divisor class Y, which I may say some more words about later on. The case Y equals 0, by the way, brings us into contact with some known constructions. So one possible F-theory construction of this family of models is to un-Higgs a charge 4 U1 model that was studied, that was constructed and studied in this paper. From the field theory point of view, it's possible to view this family of models as a Higgsing of the Tate SU4 times SU3 times SU2 models, if you Higgs on this particular choice of matter. However, to my knowledge, this isn't the so this procedure of Higgsing is not necessarily realizable for arbitrarily large. If we tune the parameters characterizing the geometry to large values, it may not be possible to realize this particular gauge symmetry construction by this Higgsing procedure that is suggested by the field theory point of view. So the construction that I'll be working with is starting with the U1 model, charge 4 U1 model, unhiggsing it, and going from there. And another limit that I should mention is the limit in which the divisor class Y is set to be trivial, in which case the model agrees with a mild generalization of the F11 toric hypersurface models studied by these authors. Now, the spectrum of these models includes the MSSM spectrum, but it also includes some exotic matter representations. And so an interesting question one could ask is, given the fact that we've arrived at this sort of generic matter spectrum for a particular standard model-like construction, is it always the case if you're to randomly choose one of the vacua that you could construct, namely a particular choice of characteristic data that gives you a particular Calabi-Yau, will you always land, or more probably land, on a case where you have the exotic matter spectrum populated in addition to the MSSM spectrum? So that's a question that I will come back to towards the end of the talk. The realization of this model is going to be in terms of, so the model can be realized as a Weierstrass model using this data, but it turns out that for the purposes of resolving the model and moving on to the M-theory Coulomb branch to do calculations, it's much more convenient, at least from my point of view, to work with a realization of the model as a cubic in P2. So this brings me to one of the first generalizations that I'm going to point to. The technology that we use to compute flux vacua, and in particular compute flux backgrounds, is something that isn't limited necessarily to a Weierstrass model presentation. It can be generalized to additional types of projective bundles, with this cubic in P2 model being a particular realization of a more general possibility for realizing the F-theory vacuum. So the cubic equation is this equation. With all parameters generic, this represents a realization of the charge 4 U1 model. And if I set A1 and S3, these two parameters equal to 0, this effectively unhiggses the model to exhibit the gauge symmetry SU3 times SU2 times U1 with the entire thing quotiented by Z6. Now, as a hypersurface equation, we should view this as cutting out a hypersurface inside of the ambient projective bundle, which I'll call Y. This is a projectivization of a sum of 3 line bundles constructed over B, and their dual divisor classes are given inside of the Schau ring of B, are given by these particular linear combinations of the characteristic data that I mentioned on the previous slide. So one thing I'd like to draw your attention to here is that this, if you compare this, for example, to the usual Weierstrass model formulation, this is not, it's rather different. If these were coordinate, the usual coordinates one would use is X, Y, and Z. This is what the notation that's often employed in the literature, and the divisor classes associated to the hypersurface equations X, Y, and Z equals to 0 would be powers of the anti-canonical class. But here you can see there's a more general construction that we're forced to use. So it's possible to find a resolution rather easily in this cubic in P2 presentation. It involves 5 blowups, and I'll suppress the details here in the interest of time. One feature I would like to point out is that this construction, at least this resolution, emits a rational but not holomorphic 0 section. So it has because there's a U1 factor, as we would expect, there's an extra generating section. And the 0 section, in addition to the generating section, both of these things are rational as opposed to one of them being holomorphic. And I should say that when Y is non-zero, they intersect non-trivially over particular codimension 2 loci inside of the base, and that locus is dictated by, it's controlled by when y, it's controlled by the intersections of y with other divisor classes in the showering of the base. Okay, so let me say a few words about flux backgrounds for the resolved Calabi-Yau fourfold. On the previous slide, I discussed a realization of this model as a cubic in P2. We can get a resolution that involves 5 blowups. So what we'll need now in order to compute flux vacua, and this is really, I'm just reviewing, in some respect, I'm reviewing a story that's rather well known, but there are some new features here. So what's necessary is to, if we want to compute the chiral indices associated to various matter representations in appearing in the spectrum of the theory, we need first to locate particular divisor classes. These classes are associated to surfaces inside of the base. They're codimension 2 loci, or the classes of codimension 2 loci. Sorry, I shouldn't say they're divisors. They're more properly thought of as intersections of divisors. So we have these codimension 2, the classes of these codimension 2 loci inside of the base. And if we integrate, so one way to formulate this is to treat G as a cohomology class in H4 of, I'll call the resolved fourfold X tilde on this slide. And if we integrate G4 over this particular cycle inside of the base by some results that have been well studied, and I direct you to Timo's very excellent Tazi lecture notes for review on the subject, it's possible to compute the chiral index of a representation R by performing this integral. It turns out that the relevant part of the cohomology, which the cohomology for X will admit some orthogonal decomposition into different parts. The relevant piece for computing the chiral indices is H22, so-called H2, 2 vertical. And this is defined to be the span of classes in H11 wedge with H11. So I'll introduce seems something got cut off here. I'll introduce a basis of divisor classes, which I'll denote by D sub I, capital I, where I can take 3 particular values, types of indices. If I is equal to a capital Latin index, it denotes a section, and in particular that something like A in this notation will be for the particular class of Calabi-Yau varieties in which I'm interested in. There's only 2 types of sections, the zero section and the degenerating section. Another type of divisor can be the pullback of a divisor in the base, and that will be denoted with an alpha. And finally, there can be so-called Cartan divisors denoted by a lowercase Latin index. So given this notation, it's possible to write down a class associated to the flux G. I'll denote that by G hat, and expand this class in a basis of these guys and compute the integrals of this sort. I can use Poincare duality in principle, to find classes associated with the cycles over which I'm integrating, and treat the integral as an intersection product. And that should give me, for a particular choice of coefficients, which remains to be determined by some means, in principle, it's possible to compute the chiral indices associated to a representation R. Now, there are a few constraints that have to be imposed on a choice of flux background in order to ensure, in M theory, to ensure that the flux background lifts to a quote-unquote good flux background in F theory, namely one that preserves Poincare and gauge symmetry. These conditions are the following. So I have to have theta with any legs along the alpha direction. So if I set these indices, I and j, at least one of them or possibly both of them, to Greek indices, then those flux integrals should be equal to 0. And if I impose these conditions in the family of models in which I'm interested, namely, so the class here is a class of Calabi-Yau fourfolds with a single generating section, and most generally a rational as opposed to holomorphic zero section, I can write down a very convenient formula where I've incorporated these constraints explicitly. So namely, theta ij is equal to the coefficients g superscript kl, and this is contracted into a particular tensor, omega bar, where omega bar is defined. You can view it as it's a leading order in some sense. It's a intersection product among four divisors, plus a number of corrections that explicitly ensure that these conditions are satisfied. So this is a convenient expression. To my knowledge, an expression like this hasn't been written down in the literature before, but it's simply a matter of doing some linear algebra and exploiting various relationships among the intersection products given the presence of an elliptic vibration structure. Okay, so theta ij, as I mentioned, are computable via intersection numbers or intersection products and the showering of the resolved Calabi-Yau manifold, or I should say variety, I suppose. In the special case that the resolution is a resolution of a singular Calabi-Yau, which is a hypersurface of a projective bundle of this sort, where I'm taking a linear the projectivization of a direct sum of various line bundles, then it's possible to apply push-forward technology in a very explicit fashion, where the push-forward map, it's the push-forward with respect to the projection that I use to define. So I should use phi. Really what I should write here is phi. That's what I mean implicitly. There's phi should be a composition of the map, which is the blowdown, and then further the map, which is the canonical projection to the base. It's possible to take that composition of maps and push forward the intersection product, compute the push forward of the intersection product with respect to that map to the showering of the base. And what I'll wind up with is an expression for all of these quantities in terms of intersection products done entirely on the base. So there's a very nice theorem that we can use. This theorem is a mild generalization of some work that was done previously. And the theorem says that given a collection of line bundles over the base, and this really can be generalized to an arbitrary number, but for here, I'm just going to use the case where there's three of them, and a formal power series, which is defined in the showering of x tilde. Well, sorry, in this case, it's the showering of the projective bundle. So here, just to be very clear, I'm discussing a push forward with respect to the canonical projection from the ambient projective bundle down to the base. If I want to talk about the blowups that are necessary for the resolution, there's additional push forward theorems that I can cite, but I'll just mention this one here because this is where the real meat of the generalization is. If I have such a formulation of my singular Calabi-Yau x, and I have some class inside of the showering, which I can represent as a formal power series. And so in particular, this accounts for not only polynomial, but also rational expressions. Then there's a very nice formula that I can use where I compute the push forward, and the push forward of this guy, where I'm substituting the formal variable t with h, which is the first Chern class of the line bundle associated to the projectivization. The push forward of this guy can be expressed as a sum over various quantities involving the divisor classes of the line bundles that define this vibration structure. So this is a new result to appear. Also something to my knowledge which does not appear in the literature and is extremely convenient for computing very complicated intersection products in terms of straightforwardly, although possibly not practically without the aid of a computing tool in terms of intersection products on the base. There's also a similar theorem for exceptional divisors, which I will not show explicitly right now, but I'm happy to discuss this in more detail for people that are interested. In any case, combining these things, it's possible to compute all of the flux integrals theta ij completely explicitly and formulate them in terms of intersection products on the base of the vibration. So in order to bring this story back around and actually recover information about the chiral spectrum, um, if I have the ability to identify the coefficients Cij that I mentioned earlier, the Cij, then of course it's straightforward to compute the chiral indices. But if I don't know that information ahead of time, one thing that I can exploit is the fact that there are explicit expressions for the flux integrals theta ij, which come from one loop calculations done in the context of a 3D Kaluza-Klein theory that's given by the compactification of M theory. It's the low energy effective description of M theory compactified on the resolved Calabi-Yau. And I can match the geometrically computed theta ij's with the low energy 3D expressions using the fact that I know that these are some linear combination of the chiral indices. So one thing that is, well, the key point here is that if I want to disentangle this relationship, I can make use of the fact that there are linear relations among the theta ij's that I compute in the M theory compactification, which are basically the geometric manifestation of the anomaly cancellation equations by the Green-Schwarz mechanism. And so what this means is that if I compute all of these guys in M theory, and I figure out all of the linear combinations that exist among them, excuse me, the linear constraints that exist among these quantities, then it's possible to create a linear system in which I can solve by performing this matching explicitly. I can solve for explicit expressions for the chiral indices in terms of some linear combination of the theta ij. An interesting comment that I'll make here is that in the case of a rational zero section, it turns out to be the case that the region of moduli space in which one is working and the resolution is one in which the kk scale, or the kk mass, if you like, is comparable to the masses of one of the BPS protected states on the Coulomb branch. And so in this case, the formulas, the 3D formulas for theta ij, the flux integrals, are a little bit more complicated than usual, and they may jump by some terms. And it's necessary to account for these jumps, which are really incorporating the contributions from KK modes in order to do the matching correctly. So if I'm going to carry this procedure out geometrically, I need to know precisely which of the states are which of the states in the BPS spectrum have masses that are larger than the KK mass. So having said all of this, let me present a few selected results. One selected result that I like to showcase here is the SU5 tape model, which includes generic matter in the fundamental and antisymmetric representations, two-index antisymmetric. And using this technology, it's possible to compute the chiral index for both of these representations in a fairly full generality. So this formula applies for any smooth base and any divisor carrying the SU5 that sits inside of the showering of the base. And it's simply given by this expression, intersection product of the canonical class with, well, it's a triple intersection on the base with involving the canonical class and the divisor class of the SU5 divisor. The coefficient alpha is a integral, at the very least an integral coefficient that goes into specifying the linear expansion of the flux. Finally, a second result I'd like to showcase is in forthcoming analysis of the group SU3 times SU2 times U1 mod Z6 in the context of these standard model like vacua that are constructed in F theory that I mentioned earlier in the context of the Higgsing of the charge 4 U1 model. And it turns out by computing fluxes explicitly and carrying through the analysis that at least at this stage of the analysis, it appears that the MSSM and the exotic, with non-trivial exotic matter, are straightforwardly realized in F theory compactifications, and hence they're not in the swampland. And there don't appear at this stage to be any obvious constraints on the chirality, although this is a preliminary result and is pending further analysis, which will appear in our forthcoming paper. And finally, I should mention that the y=0 case results, they agree with the known results in the literature concerning the F11 model. So this brings me to the end of my talk. Some future prospects. There are various directions to go. The spirit of this project is really setting up the technology necessary to compute various quantities, and it's a very robust tool. And now that we have the tools in place, there are in principle many things we could consider. One example I'll mention, and the others I'll invite you to read and perhaps ask questions about, is finding other standard model-like constructions in which the geometric realization of the gauge symmetry is not via some tuning procedure, but rather by flux breaking. So with that, I will stop here, and thank you very much for your attention. And of course, I'd be happy to take any questions.
All right, Patrick, thank you for the very nice talk. Let's see, as we wait for more questions to pop up, let me ask one. Earlier in your slides, you quoted an exotic representation.
Yes.
That you is this something that you are saying is universally there when you have an MSSM-like construction, or was this just an example?
I won't say universally. Well, sorry. This spectrum is characteristic of this particular standard model-like construction. So
okay.
Generically, if you were to take if you were to plot out somehow the landscape of all possible realizations of this spectrum and gauge group, and you would probably land on one that had non-trivial matter in the exotic spectrum, in addition to the MSSM spectrum.
Got it. Thank you. Paul has a question. Are the number of D3 branes always positive in integral?
That's an addition. I didn't mention the tadpole constraint. The D3 tadpole does need to be imposed, but as far as I can tell at this point, and again, I want to be a little bit hesitant to make very sharp claims because there are more aspects of the analysis that are still pending. But at this point, it appears to be that the D3 tadpole would constrain the flux. It would put a constraint on the size of the flux coefficient in the form of some inequality, but it wouldn't necessarily impact. So integrality is another thing, of course, but I don't think it's an obstruction to realizing a very large class of these vacua in F theory.
Awesome. I think Wadi wants to comment on that, and then Ling has his hand raised.
Yeah, sorry, I was going to comment on your question, Cody. So just following up on what Patrick said, I mean, one of the interesting features is that the F11 model, which is what you guys studied with Jim and Miriam and Ling and others, is the model with y equals 0, which interestingly doesn't have the exotic matter. So the set of the generic SU3 cross SU2 cross U1 mod Z6 construction will have exotic matter in most branches, but the y equals 0 branch is characterized by the feature that it doesn't have those exotic matter things.
Good,
but
okay.
From the point of view of the general construction, it's not obvious what's special about y equals 0 other than that fact.
Yeah, you could ask like whether or not how large, you could try to compare the two branches and maybe see how large they are relative to one another in some precise sense. But that's right. The y equals 0 branch won't have the exotics, but the y non-zero branch will.
Excellent. Okay, thank you. Ling?
Thanks. Hi, Patrick. Thanks for the talk.
Hi.
Could you just elaborate a bit more on this push-down formula that you gave in, what goes into there?
Yeah. So there are various maps that one, in principle, defines from the. I mean, if you start with the smooth Calabi-Yau that you got by performing some resolution, so there's various maps that one can use to canonically map various aspects of the geometry back down to the base, right? So if you view each of the maps, right, one set of the maps includes the blow-up maps associated with the resolution, and then there's another canonical projection from the. Really, you should view it as it's descending from the canonical projection of the ambient space down to the base. So let me call that pi, and then you could maybe denote the remaining maps by f. The push forward is simply taking some expression in the Shao ring of the resolved elliptic Calabi-Yau, which you can represent as some formal power series. In principle, it could be a rational expression, and replacing some terms inside of the power series with additional terms.
Right.
And they all look like moments like the summands in this expression. So there's additional maps which I haven't explicitly written down in the slide for that are associated to the blowups, but you can play the same sort of game. So you apply, if you do 5 blowups, you start with a push forward down to right. You start with x5, which is after doing 5 blowups. You can do a push forward of any expression in the Chiral ring down to x4, the Chiral ring of x4, and that involves replacing elements in the power series formulated like this with these moments, which are constructed in terms of other classes that are pullbacks, and then you just iterate this process until you have some horrible mess.
Right. So is it philosophically different than, for example, if the ambient space was a toric variety, or at least a toric hypersurface vibration? Then oftentimes what we can do is just essentially write down a quotient ring that captures, in some sense, all the standardized and ideal relations and the linear equivalence relations of the ambient space. And if you are, in that case, interested in at least intersection numbers of divisors that come from the ambient space, then it's just the, in some sense, recursively use linear equivalence and standardized and ideal relation to eventually reduce your intersection numbers to a bunch of things in the base times a well-known intersection in the fiber.
Philosophically, I'm not sure how different it is. I think the methods do agree when you can formulate the Calabi-Yau as a hypersurface inside of some toric variety. But if the base is not toric, then I'm not sure how one would go about accessing the, for instance, the analog of the SRI. I think there is a generalization of, and you may have even mentioned this in one of your paper with Timo,
exactly.
I believe.
This is what I was
So if it's possible, maybe you could tell me. I don't know how tractable it is to compute the SRI for a non-toric base, for example. But
so in our case, all you needed was just knowing the SR ideal of the fiber coordinates, if you wish, which I guess is in general also, if you don't have a toric resolution, then these kind of relations just essentially come from your blow-up procedure telling you which coordinates parameterize a P1 or P2 and can thus not vanish simultaneously.
So your construction was for general base, and it doesn't need
you
to be
could
toric.
Easily generalize that. So what we said that you needed was just the full linear equivalence relation between divisors on your fourfold and the product of divisors which you know are trivial in the Chiral ring. If you know these two data, then you can construct the quotient ring and allow you to do these kind of push forward computations, at least for vertical fluxes. So actually the other question I had for you would be if you can generalize, or if you have thought about generalizing that to fluxes or intersection numbers involving Chiral cycles which are not just products of divisors.
Well, so this let's see. Yeah, it's a little bit more subtle. I could maybe say some things, but I haven't thought very much in depth about trying to generalize this for things that aren't products of divisors.
Okay.
But I think it may be possible in some cases. And it's something that perhaps I won't say there's an obstruction that's obvious to me, but I haven't thought about it in detail yet.
Okay, great.
As far as your first question, I think in principle probably I wouldn't be surprised if these procedures, namely using the linear constraints and SRI versus using the push forward formulas, I wouldn't be surprised if you could show that they're equivalent.
Okay, I see.
By some computation. But
all right. Okay,
this is, in the case that they're not, this is an alternative way to do the computation.
Yeah. Okay. Thanks.
So I think maybe we can do one last question since we're running out of time. So we have one from Jan Quapiz. That is, could you comment on the Z6 factor? Do you need it due to guts, in particular for SU5, or are there other reasons for this discrete group?
It's not well, the Z6 factor is not necessary for, I don't believe it's necessary for gut groups per se, because you could view this as coming from, Yeah, you could view this as the construction as coming, at least from low energy considerations. It need not come from breaking a. Oh, sorry, I misread something. It need not come from Higgsing a grand unified group, but the Z6 is necessary in order to find a realization in which the matter is generic in the sense that I mentioned earlier, in the 6D supergravity sense. So, without going into detail, the Z6 is necessary at the very least to realize this matter spectrum as a generic feature of the construction.
All right, the very last thing, I think Miriam would like to comment on that quickly.
Yeah, actually it's related to this Z6. So for y equals 0 example, this has been shown explicitly as a prototype example how Mordell-Weil group and its geometry encodes the global symmetry of particular structure that includes U1 together with non-abelian gauge symmetry, and for y equals 0, that uniquely, the Z6 uniquely arose as a global condition on that. And another comment I would like to make is that was somewhat related also to things that Ling rose. At least, you know, for y equals 0, the analysis I believe that we've done for flux constructions, G4 construction, already was general, you know, and it started actually in the work with Ullman et al. That gave the first standard model with this y equals 0, but now we're really, you know, with conditions, I think with techniques that we developed, and also Timo Ling et al. Earlier on, within this toric fibration, we could analyze that in full generality. So just for the reference, yeah.
Thank you. Thank you very much.
Yeah.
All right, this has been a great discussion so far, but we have to end somewhere. So again, let's thank our speakers, Patrick and Martin, for the excellent talks. Just a couple of announcements to repeat to close. Junior folks who would like to give a talk, please sign up. We'd love to have you. Senior folks, please encourage your junior folks to sign up to give talks. And we can continue all these great discussions on the String Pheno Slack channel, which is still active. And if anyone needs help getting access to that, you can contact Naomi Gendler or Manki Kim from Cornell, or you can get in touch with me and I can put you in touch with those folks. So next week we'll be here at the same time, and our speakers will be Nicolo Cribiori and Paul Constantine Ullman. So looking forward to that. Thanks, everyone.